In this lecture, we're going to be discussing how to switch our path following once the UAV gets to a waypoint. And we're going to discuss briefly two methods. First, using a ball, so a circle of some radius to decide when to switch. And second, a more robust technique is using half planes. So then we'll spend the remainder of the lecture discussing the half plane and then presenting the algorithm. So to review what we're going to be developing, here's the demonstration again that we showed last time. So we'll run it a couple times. We have our series of waypoints with lines drawn in between them. And once we get to the waypoint is when we decide to switch to the next line. So again, we'll come down here and we won't switch until executing that final third line until we actually get to the waypoint. And we see that we have a massive amount of overshoot, but then we're able to get back. So let's go see how this is implemented. Like we mentioned, there's two different ways that we could decide when to switch. The first is a ball, and that's might be the way you would initially think of, is we're just going to say, hey, once we get close enough, right? So a ball is just, the idea is close enough to a waypoint, then we're going to switch between it. So here's a ball. And we call it's depicted as a circle, but in 3 dimensions, right, it's going to be a ball. So we're just saying, hey, once our distance is within a certain radius of the next waypoint, let's switch. Okay, but that has problems in that if you had a really strange waypoint here, so let's draw a waypoint WI minus 2, the aircraft might hit that waypoint, and it's not going to switch, and it maybe has slow convergence, and it's possible that it misses that ball entirely. The ball's too small, or our aircraft isn't aggressive enough. Maybe there's wind, and we end up missing the ball, and we just end up going along that straight line forever because we don't ever hit our switching condition. So this is a really fragile method. So this is fragile. So not a great technique, not very robust at all. It may miss the switching condition. So you have to be careful it's really not a great technique to use. A very much more robust way of doing so is defining a half plane through the waypoint. So in this case, we're going to define some normal vector. So this is a normal vector to a half plane. And as we come in here, that normal vector is normal to this line that I'm drawing in blue, but in reality, it's a line that goes all vertical up and down. So it's actually a plane there, and it's I should call it a half space. Oops. Or half plane. So anyway, so it intersects right there, and then it doesn't matter if we've overshot or anything. Once we're going to be guaranteed, if we're trying to follow that line between WI minus 1 and WI, we're going to be guaranteed that we're going to eventually hit that half plane, whether we're off by a little bit or a lot, right? So as we're traversing, eventually we're going to just cross that plane, and then we know we're going to switch to executing the next line, right, wherever we end up crossing. Okay, but that gives us a really nice, robust method of switching. Okay, so let's jump in. We're going to be done talking about that ball. We're going to now spend the rest of our time talking about that half plane. Okay. So, want to review one concept with our dot product, right? because we need to decide how do we know when we're in a half plane or not. So we have this normal vector, but how do we use it? So if you recall, we have A transpose times B is equal to, we have the magnitude of A times the magnitude of B times the cosine of the angle between A and B. Okay, if we look at this equation, we can see that the magnitude of A and the magnitude of B, these are always going to be, they're going to be non-zero, not non-zero, non-negative. They're going to be either 0 or positive. And the cosine of the angle between them is going to be either negative, 0, or positive. So it could be anything. But if we take a look at that, right, the cosine, if we plot up what the cosine is doing between pi halves and, oh, that was supposed to be a negative pi halves. Okay, negative pi halves. We have this even function that's going to be positive. Then it switches down below and goes below 0 when the angle is greater than pi halves or less than pi halves. So we know then that A transpose B, and again, if we just look at the angle, so now we're plotting the angle as a vector. So if we say here's the angle, so this is the angle between A and B, right? And as we move around, now the angle is going to be over here. So if we're in the same half plane, so if this is vector A, all vectors that are in the same half plane as A are going to be above the x-axis right here that I've drawn. So all vectors that point in this direction are going to be in the same half plane as A. So the angle between them is going to be, if we look at the angle between A and these vectors, it's going to be all those vectors down there to there. There's pi halves, negative pi halves to pi halves. So this is the region that we care about in terms of defining the same half plane. So if we now look at our dot product, and we say that if this is greater than or equal to 0, this implies that we're in the same half plane. If A transpose B is less than 0, we're going to say this implies that we're not in the same half plane. Or that B is not in the same half plane as A. Okay, so that's a nice test to see. So now we could test any point right here, and we could say, hey, this is our position P. If we say, here's the vector from WI to P, we can look to see if it's in the half plane by just looking at the P minus WI transpose times NI. And if that's greater than or equal to 0, then time to switch, right? So we've crossed that half plane. Okay, so here we have it. Now we're going to just look at the definition of this half plane. So given a point R in 3, so in this case our R would be WI, and a normal vector n, so we wrote that as ni, we can define the half plane, and again it's a function of r and n, by all of the points P such that the P minus r transpose times n is greater than or equal to 0. So just exactly what we were talking about, right? So we're going to define a few more things. We'll say that we're going to define a unit vector pointing in the direction of WI to WI plus 1. So if we erase some of these markings, this unit vector, we're going to call it QI, is from wi to wi plus 1. So then if we looked at a vector going from a unit vector from wi minus 1 to wi, this would be what we call qi minus 1. Okay, so the unit normal to the 3D half plane that separates the line, this guy from this guy. So we're looking at line 1 and line 2, right? It's just given by, and we can define this normal as, what we're doing is we're just basically taking the average of qi minus 1 plus qi, right? Well, we're adding them together and then we're dividing by the magnitude. So we're taking the average vector of the two. So that's how we define this Ni. Okay. Now the most important thing that we have here is that the MAV tracks straight line paths until it enters the half plane. So that's our control strategy. So we're going to track line 1 until we enter the half plane, and then we'll track line 2. And we have a really good test, right? So, and I should maybe just highlight the actual test. This test for when we're in the half plane. Okay, so we have a nice straightforward test. We can test whether we're in the half plane. Once we've crossed into that half plane, we'll start executing the next line segment. So now one thing that you need to be very careful about are singularities. So we're dividing by the magnitude of qi minus 1 plus qi. And that's so that we can get this unit vector. But we need to be careful. We'll make sure that we're not causing any problems. So let's look to see when is that going to be equal to 0? So when is there a singularity? i.e., when does qi minus 1 plus qi equals 0? Wow, that was the ugliest closed parentheses. Okay, so we need to decide that because we don't want to be dividing by 0. And so, because if, so this is going to happen, right, when qi minus 1 is equal to the negative of qi. So, in other words, if we have 3 waypoints, and we have, oops, we're going to call this wi minus 1, this is wi, and this is wi plus 1. So wi minus 1 is moving in that direction, right? And then wi, or I should say q sub I minus 1 is moving in that direction, and q sub I is moving back towards it. So in other words, this happens when the path folds back on itself. Right? Because if we were going to draw what we're doing, we're executing from wi to wi minus 1 to wi, and then we're going to go backwards to wi plus 1. So we're basically executing that same path segment a couple of times. So we have a choice of what to do. So we have a choice here. And our choices are, one, we could skip wi altogether. So if we had, for example, a wi minus 2, since let me erase that red line, we could instead just go to wi minus 1 and then to wi plus 1. So we skip wi. Because we're just saying, hey, we're going to be coming straight back, so there's no reason to do it. Okay, so that's our first choice. Our second choice our first option, right? Second one is we could visit WI before going to WI plus 1. And so assuming that whatever planner is giving us the series of waypoints we need to visit, we're going to assume that it knows that it's good to go towards that WI. So what we're going to do is we're just going to go ahead and make sure we visit. So if we come here, we'll end up, the green will go through and visit, and then we'll turn around and go down to WI plus 1. So that's the strategy that we'll employ. And there could be any number of possibilities in between. Maybe you go halfway, maybe you go a quarter way, right? Before deciding to circle back on yourself. Okay, so in this case, we still need to define our normal. So our normal, in this case, normal I, we're just going to let our normal I be equal to QI minus 1. So we're just going to keep going in that direction. And we'll let the point R be equal to WI. So we'll just keep going in that direction. The normal, so this, if we draw an orange, this is where our normal vector will be. Okay, and so we don't switch until we're past that WI. Excellent. So now we can talk about the algorithm, and I want to make one quick note. This algorithm does not deal with the singularity. So you'll need to add that logic in. But it has most of the components. The first thing to notice about this is that it's actually fairly simple. So as we come in, where the input to this algorithm is just our series of waypoints that we're going to be traversing. And we require that n is greater than or equal to 3 because we're going to be switching between them. If it's not, then we might as well just send on over the 2 waypoints that we receive. Okay, so if we have a new waypoint, then we're going to initialize the waypoint index to equal to 2. So I is equal to 2 at this point. So this assumes 1 indexing, kind of like MATLAB. If you were to do 0 indexing like a Python, you might set I is equal to 1. Either way, we're trying to get our second element. Okay, we define our for our half plane, we're actually not going to use that, right? But we have our QI minus 1 is just the vector, again, pointing from WI. Oops, I don't want to. WI to minus 1 to WI. So we have QI minus 1. We're going to define QI. Again, it's just this vector. We define our normal. It's just this vector, right? And we define then our switching half plane, where we're going to switch based on WI. So that would be what we normally say is our R value. We switch based on WI and the vector NI. So if our point is in this half plane, so this is really important. This is when we switch. This is our switching logic. If our point is in the half plane, then what we're going to do is we're going to increment I to be I plus 1. So then we'll start working with the next waypoint to follow that waypoint until we reach the end. Okay, and at each time step, we're going to return really this R and the, oh, I don't know why it's returning the R and QI minus 1. But now we know we can check this and we can publish the path to be followed as WI minus 1 to WI. All right. And this is just, again, showing what we saw previously, right, where if you define a path like this, so here's our WI I guess I should call it 1 for the 1 indexing, W1 up to W3, W4, and then it repeats to W5 being the same one, same as W1. So the biggest thing you see here is that we have a decent amount of overshoot. So we don't exactly follow the path, but it's a very simple, straightforward way to execute the path from W1 all the way up to W5. So there you have it. Our first technique for managing our paths, or managing the series of waypoints that are given to us to follow.